Session of ERESS. All the talks in this session are kind of different in terms of their science topics, but they all have this consistent theme of tackling problems in a probabilistic manner. So even if you don't do any of the research shown here today, hopefully you'll get something practical out of all of these talks. Our first speaker is Ruth Angus from University of Oxford, and she'll be telling us about periodices and K2 data while marginalizing over systematics. Take it away.
Yeah, thank you for having me here. So I'm going to talk about some work that I've been doing with Dan Mackie and John Johnson at the CFA. And having worked closely with John Johnson, I can say regarding his imposter syndrome that he does an excellent Lady Macbeth, and Meryl Streep really stole the Oscar off him. So a couple of years ago, Kepler spacecraft broke down, and it's been recommissioned as the K2 mission. And now it only has 2 functioning reaction wheels. And it slowly drifts about the foresight, and Kepler has to fire its thrusters to correct the slow drift. So the stars themselves are drifting over the CCD, and the precision of Kepler photometry has decreased. So we need to figure out ways in which we can use Kepler data, K2 data, and still conduct the same level of science as we were doing before. So this is a video of what K2 data looks like. This is sped up. This is a tweet, actually, by Geert Berenson, who made this Kepler bot. And it tweets out videos of K2 data every now and again. And something that you can see in this video is that there's this sort of periodic motion going on. And that is the regular 6-hour thruster firing of the spacecraft. So if you're interested in periodic phenomena that's around 6 hours in period, you need to be really careful when using K2 data. There are other systematics in there as well, not just the 6-hour thing, but this is just, it's obvious by eye, it's clearly bad. In an ideal world, we'd just stick Kepler on a tripod. But assuming that that's not going to be possible for the next few years, we need to look to other methods. So in February of this year, a paper appeared on the archive which was the first K2 exoplanet catalog. It was published by Dan Mackie and collaborators. And their approach to searching for exoplanets in K2 data was very different to previous approaches. Previously, people had developed very excellent detrending algorithms. They detrended the data, and then they searched for exoplanets using box-free squares in this 2-step process. What Foreman Mackie et al. Did was they did the whole thing in 1 step. So they built a systematics model and searched for exoplanet transits at the same time. So what they did was they downloaded all 21,000 Kepler light curves from campaign 1, and they did PCA on those light curves. Then they saved the top 150 PCA components, or eigenlight curves as they called them. And for each K2 light curve, they modeled the light curve as a linear combination of the top 150 eigenlight curves plus a transit model. And in that way, they were able to recover exoplanet transits whilst marginalizing over the systematics model. And this method was extremely successful. They managed to find 36 exoplanet candidates, and Ben Monte led a paper following these candidates up. They confirmed 16 of them. So this was a fantastic new way for finding exoplanets in K2 data, which did really, really well. So the next step was to take those eigenlight curves plus the transit model and to switch the transit model for a sinusoid. So now what we're doing is for each K2 light curve, we're reconstructing the light curve using a linear combination of the top 150 eigenlight curves plus a sine wave. We're finding the amplitude of that sine wave. We're doing this over a grid of frequencies, and that's how we construct a periodogram. So it's just a periodogram as you know it, with a systematics model folded in. And it's called the Systematics-insensitive periodogram, SIP or SIP. It has a sweet logo. So there are lots and lots of periodic phenomena in K2 one of the most exciting ones is asteroseismology. And the SIP works really, really well for asteroseismology, as I'll demonstrate now. So this is, in the top panel, a long-scale periodogram of raw K2 data. And you can see that there is a big systematic feature at about 50 microhertz, and that is produced by the 6-hour thruster file, which is very regular, and it's got harmonics in there as well. The middle panel shows a long-scale periodogram of Van der Berg and Johnson detrended data. So this is a light curve that has been detrended, and this is the long-scale periodogram of it. Those thruster firing signals are still very dominant in that periodogram. So the detrending method works really well for searching for exoplanets. But if you're interested in preserving stellar variability, you might want to think more carefully about what you're doing. The SIP is the bottom panel, and it shows very, very clear giant acoustic oscillations. This is a red giant star in K2 campaign 1, which we're able to pull out the oscillation modes for. So giant asteroseismology is one of the key scientific goals of the K2 mission. And giant asteroseismic modes really lie in a regime that is affected by K2 systematics. So if you're doing K2 giant asteroseismology, the SIP is exactly what you want to do. And asteroseismologists measure fundamental parameters of stars. They measure the large frequency separation. They measure that from the periodogram. So they really don't want to be picking up those systematic features. So we've used the SIP to identify some more giant candidates, and you can see here these characteristic cone-like features produced by the giant oscillations, and no systematic features whatsoever. It's also useful for stellar rotation. So on the top panel here is a rotating star, and this periodic variability that you can see in the light curve is produced by star spots that transit the face of the star once every rotation period. And you can see by eye that there's a rotation period of 2 or 3 days for the star. The top panel is, again, a Van der Berg and Johnson detrended light curve. The middle panel shows an autocorrelation function, which measures a rotation period for the star of about 3 days, which you can just see by eye that it's probably right. Probably about 3 days, you can see it in the light curve. And then the bottom panel shows a long-scale periodogram of the detrended light curve. And this periodogram really is picking up systematic features in the light curve. If you automated a rotation period measurement method and were just automatically producing long-scale periodograms from detrended data, you would very, very often be susceptible to these systematic features. And you can see that there is a peak at about 3 days, but it's not even the second largest peak in the periodogram. The SIP, on the other hand, does much better. So in the top panel, the raw light curve is in grey, and the black light curve is the light curve conditioned on the highest amplitude sinusoid. The bottom panel is the SIP, and you can see that there is no signal at these longer periods, and the SIP is able to recover a rotation period for this star. Okay, exoplanets. It's also able to recover very, very short period exoplanets. So Roberto Sanchez Ojeda has been leading some work to discover short period exoplanets using Fourier transforms, but he is not able to discover any planets around the 6-hour period or anything near it, so he has to throw them away. He's not complete. So this is one of the planets discovered by Roberto Sanchez Ojeda. We're able to recover the orbital period of the planet. Roberto needs to be using the SIP. We're also able to find our Lyrae variable stars, eclipse and binaries. So if you want to use SIP, you can go to GitHub, clone the repository, and start using the data straight away, using the algorithm straight away. And there's an IPython notebook there as well, which guides you through how to use the code, but it's really, really simple. It's so simple that you can fit it into a tweet. So don't use this version because it will take a bit longer. Use the version on GitHub, it's faster. And this code and this project was on the archive yesterday, so you can check out the paper, there's the number. So just to recap, if you want to do giant asteroseismology, stellar rotation, eclipsing binaries, variable stars, or search for short period exoplanets, or if you want to study any periodic phenomenon in K2 data, use the SIP. Thank you very much.
So for the principal components, do they change campaign to campaign?
Yes.
And how easy is it to measure them?
The principal component analysis has been done for campaigns 0, 1, and 2 already for you. So if you go to the paper or to the GitHub repository, you can see where to download those. You don't need to recompute them yourself. Although you could if you wanted to do something else.
Yeah, great talk, and really nice that you put that on computer. Everyone should share their code. Can you comment a bit what's the difference between these the co-training basis vectors from Kepler-1 in comparison to your ECA basis vector, eigenvector?
So it is similar. They used only the top 4 components because the systematics in the original Kepler data were nowhere near so bad. And they also used stars that were nearby. And we don't use stars that are nearby, we just use all of the light curves. So those are the main differences.
So can we use to get the reliable data on the sine and time variability of rotating stars?
So if you want to do sine time variability, you mean differential rotation, or?
Yeah, something like that.
So yeah, I mean, if you're interested in measuring rotation periods from light curves, then the SIP would be a great thing to use. In practice, for measuring rotation periods, what I would probably do would be to use the SIP, but also to compute an autocorrelation function of a detrended light curve. So, and then just compare those and look at the light curve by eye. In practice, that is what I would do. I wouldn't use the SIP by itself, but I wouldn't recommending for stellar rotation. I wouldn't recommend using any one method on its own anyway. I think you should always combine methods.
Is there a reason that you use the first 150 components instead of 151 or 50?
It's not something that number is not something that was optimized. It was a compromise between computational feasibility and using as many eigenline curves as we possibly could. So it's a number that does very well. Using 200, you might be able to do better, it would take longer. You know, that decision is up to you. But we find that it works well with 150 eigenline curves.
Any other quick questions? All right, let's thank our speaker again.